do it within 2 hours anyway. So we'll try to go through the first 2 notebooks. The third one is based on actually using iLearn to do machine imaging-based classification, but the first 2 are the more important thing because they go through general concepts in machine learning, which is roughly speaking way more important than the example with brain imaging data specifications. So how many people here have used machine learning before? Okay, so I see a few hands. So maybe you guys can help me talk through some of these things. So what we're trying to cover here is sort of classical machine learning. As many of you may have heard, deep learning is taking the world by storm, and I wouldn't quite put it in the realm of classical machine learning, although a lot of things that are being done with deep learning has existed, at least conceptually and theoretically, for at least 50 years. It's a rephrasing, in some sense, of the word neural network. So there is a set of machine learning approaches using neural networks that people have used for a long, long time. Deep learning makes it more accessible as computation power has increased with GPUs and larger data sets have become available. And it's really, at least in terms of classification performance, gotten to the point where it supersedes many classical technologies in terms of performance. So speech recognition, deep learning has taken over. Object recognition, deep learning has taken over. And slowly it's kind of taking over a lot of things where one would have used classical machine learning in the past. But still, it's kind of good to think about this classical machine learning thing. And just to orient people, so previously we were in home courses NeuroVis. It's now home courses NeuroML. And we're looking at inside the notebooks folder, and the one thing we're going to look at is this first one, which is called, Introductory Underbar General. So that's the first one. So roughly speaking, I think this matrix captures classical machine learning pretty well, which is you're looking at 2 types of machine learning and 2 different types of data. So you have continuous and discrete or categorical data, and then you have supervised or unsupervised methods. So you have methods on one axis, and you have data classification on the other. And typically, when we use continuous targets using supervised methods, we call it regression. An example would be linear regression as a model to predict something. So you're predicting a continuous value, and you train this model up using supervised methods. So you have a data set with known labels or known outputs, and you're using that to target the learning process. Then you have categorical and supervised. So this is what we would call typically classification. So categorical as in your labels. So if I wanted to predict based on something, let's say men and women in this room. So your labels are categories, and so that's the categorical side of this. Because I know based on my training data I have a target, which is labels for men and women, I call them supervised because I can teach it when it makes errors or use that error information to guide the learning. Then there's the unsupervised side of this. So unsupervised means I don't have target labels for my data at hand. I could have a description of people over here, height, weight, gender, but I don't have anything particular to target. But I can take all of those dimensions of data and reduce that space to simpler representations. We saw earlier with the meta search that we had many different dimensions of the brain imaging data. I would say I can't really visualize or intuit things beyond 2 to 3 dimensions. I don't know about all of you, but it's really hard for me. So often I need to reduce things down to understand relations between things. And so that's where dimensionality reduction kind of comes in. When you have continuous data and you're trying to reduce the dimensionality of structures to a space where you can understand relations between them. And it's unsupervised because we're not saying that there are labels associated with these things. Now there's a space in between these two called semi-supervised learning, where you have notions or labels of some subsets of data, and then you can extrapolate those labels to things that don't have labels. And finally, in this categorical unsupervised space is the world of clustering, which is I've taken data and I break it down into boundaries or create clusters, and I use those clusters to bin things, to understand if somebody else that comes along falls into one of those clusters, and that's in this unsupervised. So what we're really looking at is this continuous and categorical refers to the target of your method. The supervised and unsupervised refers to the method. And in this Python world, Scikit-learn is one of the more popular packages in the non-deep learning side of the Python world. If you're looking at the deep learning side of the Python world, there's TensorFlow from Google, and there's Theano, which existed prior to TensorFlow coming out as a way to do various kinds of deep learning things. And now you have Keras, right? Now about 2 years, which sits on top of TensorFlow to do various kinds of higher level abstractions or even TensorFlow. So the world of abstractions in these tools and packages is always about creating core models and writing layers on top of it to work with use cases that can be simplified to higher abstraction levels. So this figure I kind of like quite a bit. It's a little bit of guidance, I would say, to help people come up with ways to look at things when they're trying to solve various problems. So some of the things, for example, I really like is when it says, do you have more than 50 samples? If you don't, it says, go get more data. So 50 samples is an arbitrary thing. And should you get more data? That's also arbitrary. It really depends on what you're using that data for. So often, if you look at the world of statistics, you hear the term effect size. So if there was something that I could look at, even just in one sample or two samples, there was a clear indication there's a very large effect size. I don't need 50 samples to create a classifier. I can create a robust classifier with smaller sets of samples. In general, most of the things we are interested in, the effect sizes are not that big. If they were, we would probably not be interested because that we would consider as a solved problem and put it aside. So effect sizes are small. We're trying to squeeze as much out of data, and instead of over-interpreting the data, you should go about getting more data. So these are kind of rules of thumb rather than trying to strictly interpret these things. And then the parts over here are mostly about how you then approach the problem with different tools that are available. So the toolbox of machine learning has many different methods. Should you just choose a support vector machine, or should you use random forests? Should you use some other classifier like logistic regression? What is it that makes you think about what choices you have? I was, I think, writing a review the other day, and I said, you know, is your results biased by your choice of method? Can you demonstrate to me that you get the same results when using a different method? And those are things important to classify. How sensitive is the answer that you're getting? Especially when you're trying to interpret things like what features are important, what clusters are coming out with respect to the method that you have used. And these methods link with each other to some extent. So for example, you may do dimensionality reduction or clustering before you do classification or regression. So these things can have an interaction, and much like many things, we now build up complex workflows or data flows of even these methods in machine. So this example uses a default data set from Neuroinformatics itself. And it's a breast cancer data set. You can, I think, load it up. It has 569 samples and 30 dimensions. So because it's a scikit-learn data set, you can call this description attribute on it, and it tells you what are the different characteristics of each thing. And it gives you some summary stats of this data and references and other things. So this is a publicly available data set. It's a tar data set primarily to demonstrate different aspects of machine learning. And we're going to use this to look at things. Now, one of the things that this data set says is that it has one target variable, which is either malignant or benign cancer. It's a breast cancer data set. And so we can look at using NumPy's unique function, what are the values in the target variable. So I can increase the size to get to, oh, there are lots. So what Scikit Learns API also has is it can create data sets for you. You don't have to really use a data set to play around with things. It can generate data sets off of distributions. So this data set generator called Make Regression says, I want 40 samples, one feature. I want one of them to be informative, so it can create nuisance features. So these are roughly saying, I'm going to play around with data that I create, that I have answers from, that I know what things are like and see how methods behave. The world of real data is very far from that world. Most of the time, what works on toy and noisy data breaks down for real data. So it's important that as you're doing machine learning, really try and collect as much data as possible. Don't apply machine learning just because it's the exciting thing to do for papers. Use it when it's absolutely necessary and you're doing certain things. So I'll tell you, give a few examples where we use machine learning. So we do work where we predict treatment outcome based on brain imaging or other data. So we have data sets which either have brain imaging or behavioral and other data, but they also have treatment outcome. And what we try to do is to say, if we acquire brain imaging data prior to when the person started being treated, can we use it to predict how well that person would benefit from a particular treatment? In most of our data sets, we don't have different choices of treatment, so we can't tell you which treatment would be the most effective, but what we can tell you is whether somebody would benefit from some of those things. And for some of the brain imaging ones, those data sets are fairly small. We have 40 to 50 samples for some of these things, which we have used to publish papers and write about things. Would I go to the bank and say, I've got a treatment predictor? No, that's too small a sample to cover variation in the world. So it's very important that if you have a chance to collect more data, collect more data. I know it gets hard under certain resource constraint things, but if you can, collect more data. So you've seen joint plots before. So this is just plotting this regression data, this fake regression data set using Seaborn. What Seaborn can also do is to fit a regression model to your data set. So again, this is just the plotting library, but it has a few statistical functions built into it. And at the end of the, maybe not at the end of the day, at the beginning of the day, a linear regression model is effectively this. You're trying to fit a set of parameters to your dimensions of data that help you predict some variables from some output, from some input. Now, in this case, in this fake data set, you only have one dimension. With one dimension, I wouldn't even think about machine learning. I would just plot one dimension against the other one. It's easy to see whether that's a single line, whether that's some kind of polynomial that fits it, that's it. But it gives us some intuition into this. So linear regression, people like linear things, people like lines, they can explain lines. The world, I would say, is not necessarily all linear. We tend to use linear things for a lot of things because it's simple, because we want to interpret things. But one of the things we've learned with various aspects of machine learning, or various data sets we use, is that nonlinear methods often do well. We sacrifice interpretability in many cases, to use that method. So it becomes a question of what your target is. Is your target to try and explain the biology of something? Or is your target to create a black box that best optimizes some prediction? Sometimes you can mix those two things, but in many cases they're kind of separate targets. And if you're trying to make a black box, you want to make the best black box. It doesn't matter whether it uses a linear method or a non-linear method. So one of my go-to routines that I use for almost any problem that's tossed my way is a classifier called extra trees. It has both a regression function and a classification function. It's a variant of random forest. And once you have enough data, it really does well on average. It may not be the best classifier, but it really does well on average across a wide range of data sets. But that doesn't mean I wouldn't look at other methods to see how they compare. And that's one thing that you should consider when you're doing machine learning, is these tools that are out there make it very easy to run different classifiers on the same data. Don't pick the one that gave you the best performance. Instead, report all the things and show the variation in performance across those things. That's actually informative in terms of doing so. And performance itself, we'll get into prediction errors in the next notebook, is important to consider. How do we classify, or how do we think about performance? So let's look at linear regression and scikit learning. It's as simple as importing linear regression from model. You create an object and you say, fit my data. So it fits the data. Oh, I haven't loaded the data set somewhere. I should hit enter on these things. Okay, now it has loaded the data. And since it's a linear regression, I can ask it for its intercept. And since this only has a single input feature, this is my fake data set, it gives me one slope parameter. So a line, all I need is a slope and an intercept to tell me how that line behaves. And now I can look at how that line fits in with the data. So before I ask anybody to do an exercise, how many people are still left connected to their notebooks and have pulled this up? 2 people, 3, maybe 3. How many people are left with connected notebooks? I feel like for the sake of time, I should kind of go through this, and if you can follow along with your notebook, do it, but maybe we leave the exercises for people to do offline. So the main thing is this exercise extends this idea that you're not just fitting one variable to one output variable, but you can actually use, it's a linear regression model, you can fit lines or hyperdimensional lines or planes to multidimensional data. It's still a linear model. And one of the nice things about the linear regression model is that it's very fast. What's not nice about a linear regression model? Okay. Yes? It doesn't describe nonlinear. It's a linear. The word linear is all over the model, right? So it's going to erroneously fit nonlinear data. So we will again use things that you have seen to describe different components of this breast cancer data set. So a few things we plotted over here are radius, texture, and concave points, and symmetry. And this responds to cells, or the images of cells and the information that was extracted from it. So if I were to just look at this, there might be a few things over here that might give me separation between these classes. If you're just looking at this, some things. Maybe radius a little bit. It doesn't give me perfect separation between the classes, but it's reasonably separated on some of these dimensions. There's a fair bit of overlap. Now, what should we have done to plot this a little better?
Decrease opacity?
Decrease opacity. Right. So if we use opacity, we can decrease it so that we can actually see that there's a whole bunch of blue dots over here that overlap. But in general, there might be something in radius that shows a nice separation between the target classes. Okay. So as with most things, scikit-learn really makes it really easy to apply different kinds of classifiers. So here, it's using something called a k-neighbors classifier. It's a very simple classifier, and we can fit this data, and we can even ask how the separation plane that the classifier determines fits with the data. Not great, but again, it uses the separation mostly based on radius to separate out the classes. So again, I'm not going to say that you should use this classifier. The intent here is that it's very easy to run a classifier on the data. So what are the principles that have come out so far in terms of running? So we've run regression and classification. So what made it so simple to run this, besides saying scikit-learn is a package that makes it simple? How's the data represented that goes into this? It's two-dimensional. So you have samples on one axis, and you have all your features on the other axis. As we're thinking about these classifiers, what makes it complicated? The multiple dimensionality. So if you've heard of this term curse of dimensionality, that comes up in the world of classification quite a bit. So what's one way, I think Wikipedia has a very nice description of the curse of dimensionality. So what happens with curse of dimensionality? So we can think about two-dimensional data, right? 2 dimensions, and you can look at distances in 2 dimensions. If we extend to 3 dimensions, you can look at a sphere within a cube. Now, if we take that analogy and extend to multiple dimensions, then the amount of space occupied by that sphere, or that hypersphere, relative to the height of the cube, is tiny. Which means as dimensionality grows, the sparsity of points increases very, very rapidly. So distances become less meaningful as dimensionality grows, especially Euclidean distances, because we can compute Euclidean distances very well. We can have a 1,000,000 feature dimension and another 1,000,000 feature dimension. Euclidean distance, very easy to compute. But as that dimensionality grows, that distance becomes less meaningful to separate out things. Which is why people work on the next set of things we're going to talk about, which is reducing dimensionality as much as possible. The other problem has to do with an interaction between dimensionality and these classifiers. So as with brain imaging data, let's take brain imaging data as an example. So we have voxels nearby that show very similar patterns of activity, especially as we run things like smoothing on our other operations of the data. They're inherently correlated in terms of their responses on other things, which means that you have 100,000 voxels in a brain imaging data set, but many of them bear strong relations to each other. And many of these classifiers or regression models are not good when features share strong correlations with each other. So that's another reason to think about why you should use different classifiers. In the linear world of things, you have a whole bunch of classifiers which use regularization. Regularization is a way of forcing classifiers to behave in certain ways. One example was you could have a linear model, and you could have a regularization factor over it, which forces that most of the weights are close to 0. A linear model of that kind is called ridge regression. So if it basically says, I'm going to say that only a few features can have large weights. Because in linear models, the strength of the weights, whether positive or negative, means that feature is more important than another feature. When you have correlated features, this is going to throw a wrench into that problem, especially if you have thousands of correlated features. So it can run into issues there. Then there are different ways of representing weights. So lasso is another linear model. And there it says, I'm going to force weights to 0. So that regularization parameter in lasso takes weights and forces them to 0. It says, I can only have a set of sparse features. So these are all different models with different assumptions. So it's great that you can run these things. And one of the things I would highly recommend is for any problem that you have, explore the space of these models, see what they do with your problems. When we cover prediction errors, we'll show you how to protect yourself against that exploration. And finally, when you can report things across these models, I think it actually makes for a stronger paper or result. So in the world of unsupervised stuff, one of the most common ways of clustering is an algorithm called K-means. It takes data and it breaks it down based on distributions or clusters it creates, and it likes certain things. So K-means is not going to work for all kinds of data that you have, especially nonlinear shaped clusters. K-means really likes spherical shaped clusters where the mean of the cluster is close to the cluster center. So that's the kind of information you want to glean from each algorithm, is what are the assumptions that are coming out of these models. Now, a simple workshop like this isn't going to cover all of these assumptions and models. So if you're really interested in applying machine learning to these things, I would highly recommend going through Elements of Statistical Learning, which is a free online book. Pull it up. You can see right over here, it says, download the book. This does require a fair bit of mathematical knowledge. I'm not going to sugarcoat the Elements of Statistical Learning to say that it's going to be an easy read. But this does cover a lot of details of a lot of these models in terms of assumptions that it makes, in terms of things, which are often hard to find packages like Scikit-learn. So Scikit-learn will actually cover some things in their user tutorials, but it's impossible to cover the full extent of these methods and classes. And part of what you want is really to get an intuition about these methods for the problem space you're solving as well. So it's this connection with your data and these methods that's important. Anyway, it's an available book and you can download it and read through it. So here, much as we loaded the breast cancer data set, here we're going to load a very simple data set that also exists, which is the digits data set. These are handwritten digits. It's again a toy data set. I shouldn't quite say it's a toy data set. It probably forms a demonstration for many machine learning papers out there, how well they can take these handwritten digits and classify them. But this is a small version of this data set. So we're going to load it. It again gives information. We can look at the shape. This has a few more samples. This has about 1,800 samples, but it has 64 dimensions. And where do these 64 dimensions come from? Well, each digit is an 8 by 8 pixel. So they took handwritten digits. You can also see they're all normalized to fit the box. So there's a bit of normalization and processing that has gone on to say each digit can be represented in this 8 by 8. And 8 times 8 is 64, which is how you get the 64 dimensions over here. So we can plot a few of these samples. But when it comes to representing information for scikit-learn, as we just learned, it's 2D. So we take these 8 by 8 and simply create a long string of 64 dimensions, which is what this figure is doing. All right. Now, if I give this to a human, most of us would give up in about 5 seconds. Right? If I said, "Can you tell me what that row of the digit is?" We were very good at recognizing that, because we're used. Our pattern recognition system knows digits look like these. And that's the other thing with respect to machine learning. This is a data representation. And somehow, this machine has to figure out how information can be gleaned from that representation and turned into learnable patterns. So we can do one quick thing, which is runs k-means clustering. On the data. So this is trying to take that two-dimensional matrix, and without knowing anything about that these are digits, trying to infer are there clusters in this data. Oh, I must have lost connection. Everyone has? Let me just reset this very quickly. Yes.
Can you go over this again? Like, how do you get from the pictures of the individual digits, right,
to this? So from here to here. Okay. So each of this is an 8 by 8 box of pixels. If I take those pixels, 1, 2, 3, 4, 5, 6, 7, 8 from the first row, then add the next set of 8 pixels. So when I do this for all 8 rows, I get one long string of zeros and actually grayscales to represent the information. So that's how I get one row over here. So each digit there corresponds to one row over here. And what this shows is the entire data set that I've loaded up. So there are 1,700 and something, 97 rows.
So you'll take all the pixels across like this and put it on the first row?
So forget every other digit, just concentrate on this first one. So you're taking that 0, you're taking all the pixels from the first row, then concatenating all the pixels from the second row, all the pixels from the third row, and since you have 8 rows and each row contains 8 pixels, you get 64 pixels from each digit.
So that first row on that big table is 0?
Yes, I mean, I think it is. It's, they are plotted in the same order. So this is a subset of the data, right? This is not all 1,797 samples.
Oh.
Right? This is only plotting 30 samples. But yes, it's very likely that if we were to reshape that first row, we will get back 0. So that's how that data set is represented. Then what we're doing is asking scikit-learn to cluster this data set. So it has no knowledge that these are digits. The only thing we're telling it that may be informative to this thing is that there are 10 clusters. Right? We don't know a priori, I mean, we can make that decision over here for this data set, partly because we know there are 10 digits in numerical representation, so we're giving it 10 clusters. But we could have asked it for 5 clusters, we could have asked it for 11 clusters or 12 clusters. And there's a whole world of how you might determine how many clusters to set. Some of the things that you will come across are words like silhouette coefficient, which establishes distances between clusters and within clusters as a way to measure how strong clusters are. So there's, again, we won't go into details of every single method over here, but there are ways of determining how stable is your cluster. And the other place where this might help is if you have data sets on which you can validate. So do I receive, if one data set tells me that my stable point is 10 clusters, does my next data set also return that my stable point is 10 clusters? So those are ways in which you can determine whether that number, or you would rarely set that number automatically. You would sweep through a set of clusters and then determine stability constraints on those clusters, and there are methods to do that. So we've done this. So now we can look at these clusters that it has found. And without knowing anything about a digit data set, it seems to find things that are somewhat related to digits. Right? It didn't find arbitrary clusters. It didn't try and cluster things that were close to it. It's probably made a lot of mistakes. So if we were to actually look back at things that it clustered, 1 and 9 or 1 and 7, it's probably made a lot of mistakes between those two things. There's some people write one almost that looks like a 7, and some people write one with a single thing. But it's kind of interesting that this has no knowledge that these were written digits, but through a simple method of saying that there is information in these digit representations, it can figure out some details.
This is done through, where's the applications?
So it's about statistical properties of these samples. So when you write 1s or when you write 7s, statistically, they're more closer to each other. All k-means is doing is basically saying what things are close to a given sample and what things are far away. And it's saying there are 10 possible choices of samples with the clustering constraint of 10. And so it figures that out and tries to move things from one sample to another depending on how close it is to the mean of that cluster. And one of the things, again, is that initialization of k-means can have an impact on what clusters it finds. So there are many people who worked on various methods to randomize and modify the initialization factor of k-means to make it more stable. So now we can ask the question, clusters is not defined. We can ask the question, how accurate was this clustering with respect to the labels? Because we know every digit has a label. And it wasn't that bad. It's about 80% accurate, even with, so will this translate? Will you use k-means for everything? Absolutely not. But in this particular case, for this data set, the way this data set is represented, k-means does a reasonable job. Could we push this higher? Very likely with some of the tools. So in fact, the handwritten digits data set has, it's the MINIS data set, it has over 10,000 samples that's available online. This is a very small subset of that data that's used for demonstration purposes. So you can actually look at it and the performance is not going to be that. But this is still way better than chance because you have a choice of 10 possible digits. So chance would be about 10%. So we're doing really well from a classification perspective as to how well just a simple clustering approach, there's no model, there's no learning, does with saying, where does this sample belong? But could we do better with reducing the dimensionality of this data set? In fact, that might give us clues as to what's being used in terms of this clustering process. And one of the more common algorithms that's out there. Probably everybody in this room has heard of principal component analysis. It's one of the simplest methods of whitening or sphericalizing data. It reduces variance and tries to determine orthogonal dimensions that minimize the variance in the data.
And we just scramble this diagram right here, completely scramble it. Would it still be able to classify?
Yes, so k-means cluster would do fine. In fact, the previous data set that was sent to k-means was scrambled, unlike this one. So this one, this image, is actually using the known labels and sorting the data set by knowing the labels. So the original data set which we saw earlier was actually a completely random order of the digits. So it wasn't using ordering information in any way to do that clustering. So we can run PCA, and PCA gives back different dimensions. So you get eigenvalues and vectors coming from, so I should say eigenvalues and vectors. You get components and weights on those components coming back from a PCA. It uses eigen decomposition underneath to get that information. So what we can see over here is that a lot of information in this data set is contained in very few components of the data. Much of it is fairly blank down here. And that may make sense. So if we look at this data set, well, there are lots of columns where uniformly across digits you have zeros. So there is no representation of information. So if you think of a digits data set, the corners often have no information in there. The centers, depending on the digit, it may have, but again, some of the tops of centers, if I were to take, have zero information in there. And that's what's literally being reflected over here in this principal component decomposition. So what we can do is take just the first two dimensions of that decomposition, and that's being plotted over here. So the first two principal components, and then each dot is being colored by its identity. So what digit it represented. And while there's a lot of confusion between things, several things do pop out as having differences. We're only looking at the first two components over here. So we can now repeat this with 16 dimensions. 16 arbitrarily taken really for the moment. You can do various kinds of analysis on the principal components to find out an optimal set of components. So now we've reduced that 64-dimensional data set to a 16-dimensional data set. And we can again check the score. Still at about 80% accuracy. So we've taken a 64-dimensional data set, reduced it with PCA, and it can still, at least in the small sample of data, get to an 80% accuracy in putting it into the right clusters of digits. You want complete thunderstorm when machine learning is going on. So this was just to give you a general sense of the landscape of machine learning, which is you have regression problems, you have classification problems, and then you can do dimensional reduction and clustering. And they can interact with each other, because now I can take this and give it into my linear regression model and ask it to predict which label I was using. This is a 10-class problem, so many of the tools won't, because I'm predicting 10 digits. So it's not necessarily, so I don't want to put into linear regression per se, because that's a continuous prediction method. But I can use some of the other methods which can do multi-class labeling. And 17,000, 1,700 with samples in this particular case, just given what we see straight out of K-means, would likely do a reasonable job. But in many cases, pushing the boundaries of this, so the accuracy of this data set, I think with deep learning right now is 99.96%. It's incredibly good how well people can recognize accurate digits. Okay, so
Is that true for letters as well as digits?
I don't know of the letters data set, but most of these simple toy data sets, as the number of samples grow, some of those deep learning architectures can really do a good job of recognizing. In fact, cats and dogs, I think, is at 99.96% in individuals. And if you ever were to look at a cats and dogs data set, so there's one that has about 25 million images. It could be that a cat is peeking out of somebody's shoulder, and that's the level of accuracy on that data set in terms of cats and dogs. So, let's reload this one. So to me, I think this is the most important bit about machine learning, prediction error. So somebody tell me what prediction error might be. Yes, go ahead.
I was just going to say, if you trained on a certain data set and then we apply it somewhere else and you're wrong, that's a prediction error.
Okay, so I'm going to repeat that over here. So he said, if you trained on one data set and you apply it to an unseen data set that was not used in training, and you look at the error in that unseen data set, that's your prediction error. If you were to apply that model to the data set that you trained on, that's your training error. And one of the key elements is that if you increase the number of features in your training data set, even with random features, your training error is going to continuously decrease. So as you add random features to it, your training error is going to decrease. So as the complexity of the model grows, which is what we mean by adding more features, your training error continues to decrease. Whereas your testing error or your prediction error will not necessarily decrease as you add more features. So there's going to be some optimal point at which your testing or prediction error is the lowest, and then it'll start increasing again. So this is one of the key things to remember in machine learning, is that you want to test your model on unseen data. More importantly, once you've seen that data, you're done with it, really. So for those of us doing brain imaging stuff, that's a very hard sell. Because now you're saying collect more data to do more validation. So here comes the other technique, which is cross-validation, which helps you reuse the data that you have to create samples of training data sets and test data sets. And there are many different schemes under which you do cross-validation. And then one of the things that you might want to ask is, how well is my model doing? So you have an accuracy number, let's say 70% in a binary classification task. How good is that number? So we can ask two questions about it. How good is it, and whether it's significant? So the significance testing part of it simply comes from doing an analysis which says, if I were to relabel all my labels randomly, how well would my model do? That gives you what's called the null distribution of the model. And you're comparing your actual result with respect to where it fits in with that null distribution. And that tells you how significant it is. But how good is that model? Is 70% good enough? Or should it be 100% all the time? So how do we evaluate the goodness of a model? When do we get satisfied?
should not overfit as well as it should not should take into consideration optimum difference. So we can check for the other contingent matrices parameters like sensitivity and specificity.
So sensitivity and specificity are good measures or metrics of model performance. But we can use that, again, to come up with a score. So if we use it, look at something like an area under the curve, which is a way which takes that into account. That's still a number that goes between 0 and 1, right? So the question I'm asking is a little more independent of the methods, which is, at what point do you say my model is good?
When it's perfect.
When it's perfect?
Yeah.
Well, when it's perfect, it's obviously good. But that's going to be hard to reach in most cases. So where do you say, or how do you think about saying that this is a good model?
90%.
90%, okay, I hear a 90% here. It's almost like a bidding thing. Do I hear an 80%?
I think it's very problem specific because in neuroscience it's really hard to get even more than 85%. And even if it gets, it's not very generalizable also. So in this sense, it's
So I heard a few terms over there: problem specific, generalizability. So those are both good things to consider when you're thinking about goodness of models. Often when you're creating these models, as I said, you have two things that you're looking at. One is an understanding of features that are relevant to the classification, right? Because you want to say something biological about those features. And the other is, as a black box, you want to get the best classification possible. So who are you comparing that black box to? Either another black box or a human who is doing that task. Right? So in some sense, you're not looking at chance performance as your metric for goodness. Your chance performance may be your metric for statistical testing. But it might be whatever you're using that model to replace. And that thing that you're trying to replace with this new model could either be a human or could be another black box that was being used. And so now you want to know how well does this model do relative to that other model. And what might be some of the other criteria that we might use to think about model performance. So a less complex model might be worthwhile relative to a more complex model when your performance is not distinguishable between those two models. So model complexity, and model complexity comes from two things in this space of things. One is the number of features that you're putting into the model, and two, the model itself. So if you're using a random forest with thousands of trees, that's a much more complex model than if you're using a linear model. Now, if the difference between those two models is not statistically significant, I might as well use that linear model because it's cheaper to execute. So model fitting or model fitness is really dependent on the application at hand, what you're trying to target. Very often in neuroscience, the only thing we care about on the classification accuracy side is that it's reasonable, and some people use 80% as reasonable, some people use 70% as reasonable. Some people will say, I have seen models that do as good as 90%, so to me 90% is reasonable. All of those are completely arbitrary to a certain extent. What you really want to say is a comparison to either a previous published paper on that same problem or to an existing thing. So this is where, if you list that these are the performances of the different models, that's actually a good way to demonstrate how well each model is doing, because each model may have differences. If you have lots of data, there are also other models out there which actually optimize even selections across models. And so we won't get into those things here, but you can choose models optimally as part of the model itself. And then there's a class of things called super learners, which basically take the entire kitchen sink, you have a lot of data, and can figure out optimal pathways of combining things. But by the time you have that much data, you're very likely to just throw it into TensorFlow, and TensorFlow will give you a good enough result at that point in time. So to illustrate these points, we'll run through a fake data set. So this is our fake data. So one thing we can do is to say, I'm going to take this data and divide it into a training data set and a test data set. So this is the simple idea of splitting the data. And based on the training set, we will fit a linear regression model. And since we have a linear regression model, there are many ways in which one could get at information from here. But one way of getting it is to use something called the mean squared error. Another method is something called explained variance, or R squared, that you may have heard of, which also gets at. The nice thing about explained variance is a perfect model gives you an explained variance of 1. Mean squared error, a perfect model, gives you a mean squared error of 0. So the upper bound of explained variance is 1, but things that explain 20% variance or 30% variance are generally considered good models by rules of thumb that people have defined over the years. So it gives you a little bit more metric than something like mean squared error, where the upper bound of mean squared error is infinity, which is a really terrible model, and it's hard to get a rule of thumb as to what's a good mean squared error. Now, within certain application-defined areas, people have said, okay, in general, we see on this data set a mean squared error of 8 or 9, so something better than that, so lower than that might be good. But it goes back to the previous question, how do you evaluate how good the model is? And it's really going to be application dependent. And what you're really comparing it with is what you're trying to do with the model. So here we have a mean squared error of 1.48 with a linear fit to this model. Now, if we look at this model, we know that if we had a quadratic fit to this model, that would be a better fit for this model. So linear fit does well. So now we can use polynomial regression, which basically would allow us to fit quadratics to this. And we give it a degree of 2. Normally, you wouldn't choose this degree, but you would let the model figure out what this degree is. That's what you do as part of cross-validation. And we can immediately see that the model score is better, and our mean score is lower, which means it's also better. But we could also give it a 15-degree polynomial. And if we do that, we find that our model score is better, and our mean squared error is lower. Why is this not the right way to go about looking at this? So even though we have split the data into training and test sets, we're evaluating our scores on the training data. So this is effectively giving us training error, not prediction error. So now if we actually look at the fit to our test data, we find that our model score is not really very good, and our mean square error is actually quite large. So this is what we would call the prediction error. This is what we would call the training error. And as we increase the number of features in this model, our training error kept going down, but our test error crept up. So we can look at this now for the linear model. And we can look at it now for our polynomial model with degree 2. And we find that the one with the polynomial model has the least mean squared error. And this is a toy example, but it tells you that if your model matches the data well, it's going to provide the best result. The whole point of machine learning is to kind of come up with this model to do this. So one way of doing this is what's called the bias to variance trade-off. And I'm going to pull up this figure if it shows up. And I kind of alluded to this earlier when I was talking about it, that your training error keeps reducing as your model complexity grows. So if you have more parameters to fit, you are going to find a lower error as more parameters increase. So model complexity is increasing, your model is getting larger as you come this way. Your test error, on the other hand, has some best optimal standpoint at which
what is the reason behind that?
So the reason is that what you're looking for is this idea that as long as you can describe the model well, so as long as your model figures out a good model or representation for the data, that's your optimal point. If it deviates from that point, then you're going to get worse off in whatever direction it deviates. And what's happening as you increase the number of features is it's basically assigning weights to these features to fit the data better, at least in the case of simple linear models. But it's not really generalizing well to unseen data. So if you go back and look at, well, we can look at this figure because this is kind of reflective of the same thing. So we had a quadratic data set, right? And you fit a linear model to the data. It does somewhat, but it's not going to be great. If you actually fit the data with a model that it was generated from, it obviously does the best. But if you overfit the model, it's trying to fit every single point, which means it's going to do really bad for points that it doesn't see. So as a result, that model will be really, really bad. So this is, again, a toy example to think about the problem, which is that what you really are interested in is this test error. That's what you want to minimize. Now, often people will run through cross-validation. We haven't gone through cross-validation, so let's take a look at cross-validation. So the general idea about cross-validation is you break this data set into a training set, and test set. If you had lots of data, you could do this pretty easily. But often people, at least in neuroscience, we have limited amounts of data. So often what we end up doing is something called a k-fold cross-validation or a one-out cross-validation. So you'll hear the term leave one out come up in various papers. That's not a great scheme, but it's one that's used. In this notion of bias and variance trade-off, the leave one out scheme generates classifiers with reasonable bias but very high variance. So on unseen data sets, your predictability of that model is actually quite wide. But on that data set, it generates things that are close to the mean accuracy of the model. But the general idea behind any of these cross-validation schemes is the idea that you use part of the data to train your model, and you don't use that data to test it. You use other parts of your data to test it. So what implications does this have for models? Well, one might say that you want the distribution to match. Roughly speaking, that whatever you're leaving out, that on average, the distributions of those left out samples are in your training samples. It also means that the overall distribution of your data set is what the model can learn from. That it may not be able to generalize or extrapolate outside of that. So imagine I sample 1,000 people. Statistical parlance, that is often representative of a much larger population with a certain confidence interval. So if you follow polls in various countries, they don't go around sampling every single individual. We know how well polls did last November in at least the States. But what that tells you is that you have errors. And those errors can be outside. So yes, on average, they're within those confidence intervals. Most of the time, but they can still, under certain circumstances, be outside those intervals. So with cross-validations, especially with small data sets, you're still going to be limited about the generalizability of that model outside of representative samples that are similar to the distribution within that data set. So leaf PR cross-validation is the idea that you can say, so if P is 1, it's leave 1 out cross-validation. If P is 2, leave 2 out. So you leave 2 samples out, you trade with the rest. And there are many different cross-validation schemes. So leave 1 out, we talked about K-fold. You take the data. What's important is that there is no order in the data. You have to ensure that before you do K-fold. And then you split the data into equal folds of test set. So anything that's in green, that's going to be used for training. Anything that's in yellow, that's what we're going to test on. So imagine if there was an order in this data set. So that would have affected the performance of this model quite rapidly. So you want your data set to completely randomly scramble before you run K-fold. What I do like is this idea of random subsamples. Yes, it's computationally more expensive, but the idea is that you split your data, you randomly pick, let's say, 80% of your data for your training, and you use the remaining 20% for testing. And you keep doing that randomly. So each time you do that, you build up a distribution of training and testing. So instead of getting a single number at the end of the day, which tells you your mean performance, what you get is a distribution of performance of your model. And that can be quite informative of the performance of the model. Because that also tells you what are the extreme points, especially on the lower end, that you could get to, which means you could then inspect those subsamples to ask, why did my model perform so poorly in those tails of the distribution? And that might give you clues as to how those people in those tails, in those two groups, were different. And this is something we use quite a bit now when we do cross-validation. We will run 200 to 500 iterations of randomly picking 80% of the data for training and 20% of the data for testing, build up a distribution. You can report the median of the distribution as your average performance, but then you can also look at the tails of the distribution to understand how well, or what is it in that data set that gives rise to poor performance in the tails of the distribution. Again, Python being the nice world that it is, makes it really fun, easy to determine the cross-validation score. So in Scikit-learn, you simply say cross-validation score, put in the various models, X and Y, and it will compute it for you. I'm going to do the exercise. So for classification purposes, this is a useful figure to kind of keep in your head, which is that you're not getting at accuracy as your sole metric. It's important to understand false positives, false negatives, and true positives and true negatives. And these different things give rise to both the sensitivity and specificity thing that was brought up earlier. But you may want to optimize for one versus the other, depending on the target at hand. If you're doing neurosurgery, false negatives may be more important than false positives. So you want to think about what metric you use for your model, depending again on the application at hand. So if you hear the term application dependent, that's an essential part of machine learning. It really is your choice of model, your choice of features, your choice of metric, and your choice of scheme for cross-validation if you're doing cross-validation. So we can look at this breast cancer data set. We can look at something called the precision score. And I think this was updated So precision and recall, they're not sensitivity and specificity, but they're again two metrics that you both want to be high for it to do a good job on a data set. Are those good and high? I have no idea. I would have to find out what a doctor would do if they looked at these same images and label it. Right? So that's what we are comparing against, at least in the case of something. Can a doctor look at a scan, or can a biopsy on a thing detect malignant tumors directly? If a biopsy can do it, then we are perhaps comparing how fast or how accurate this machine learning is to the actual biopsy of the scan. So I've given an image versus I've given tissue. Can I get the same accuracy or better accuracy off of the image than the tissue? That's what this is comparing. This is not really trying to get at what features were important. The world of machine learning has been about crafting features. So the practical world, not the academic world of machine learning, has been about how can I engineer features that give me the best performance. And the way they test it is by collecting lots and lots of data and keep improving that feature space. The brain imaging or the neuroscience world of it doesn't have, well, till recently didn't have, let's put it this way, that much data. Now we have access to at least 14,000 samples of individuals openly available in public databases, and in private but accessible databases you have another 15 to 20,000 samples. That's a pretty large space to be in right now relative to where we were even 5 years back. So that's important to keep in mind, that there's a lot of data out there that you can use to build up things. But now if you're looking at things like my group has worked on in the past, which is treatment outcome prediction, we still don't have large enough databases in that sense. But if you were to look at diagnosis of autism, ADHD, there are some larger databases out there to do that. So it really, again, depends on the amount of training data that you have, but the good news, at least on the brain imaging side, is that these databases are growing quite a bit. So one thing I'll just point out over here very quickly is that this just used two features in this classifier. It's a simple K-years neighbors classifier. I just used two features and got 85 and 94%. What the second step does is use all the features. So again, just between these two things, it says that even when we have a held out test set, by using all the features here, we get better model performance than using just two classifiers. So very often, at least in the world of science, we will hear people say, these are good features for this particular problem. In terms of things that you run, that's a good thing, that's prior knowledge, and you can compare it to that. But this is the kind of thing that you can do quite easily. To use a classifier that can use all the features, versus one that somebody says these are a good set of features. As long as they didn't look at that same data set to figure out what those good set of features were. Right? So even features, we won't go into feature selection here today, but when you're doing feature selection, make sure that either you use nested cross-validation to do feature selection, and by nesting, what we mean is that here we've talked about train and test set. But imagine you can take the train set and do the exact type of cross-validation scheme on just that training data. So that would be called a nested cross-validation. And often people will use a nested cross-validation scheme to select model parameters, select models. So if you were to evaluate different kinds of models, and also to select features. So if you have lots of samples, it becomes easier to do it. If you have very few samples, A, just doing this is going to reduce your samples, because now you have a subset of data for your training samples. And if you're going to subdivide that training samples into further smaller training and test samples, that's going to leave even smaller samples. So when you're doing nested cross-validation, again, it's important that you have a lot of samples. So if there's one thing that you take home is get a lot of data. So once you have a lot of data, it's really a very different space of operating with these things than if you're in a data restricted space. And if you have limited amounts of data, then try to present your results as comparisons across algorithm schemes so that you give a fairer sense of whether somebody cherry-picked one single model and set of features. Because it's very easy to cherry-pick those features. You're in a research project, you run these over and over again over multiple months. And in your head, these features kind of suddenly pop out as being relevant, and suddenly somebody someday uses those features to run it. That's effectively created a bias for your model. So ensure that feature selection, model selection are all wrapped into the code that you're running to get at your performance. This is, I don't think anybody's going anywhere, so I can continue for the next 2 hours, right? Yes. So the final section of at least this thing is this idea of significance testing. So how do you know your model is doing well? So for a classifier, the idea of significance testing is, are we doing better than flipping a coin, at least for a binary classifier. So flipping a coin is 50% probability to flip a coin, at least an ideal coin. It turns out for a real coin, it's not exactly 50%. But for an ideal coin, it's 50%. Are we doing better than that? And how do we do that? So one way is to do what's called a permutation test, which is you take your test labels, or your labels for your data, and you randomly permute it. So under that random permutation scheme, your model is going to do somewhat with some number under that random permutation. And you keep repeating that. So you run 500 permutations, or 1,000 permutations, or 10,000 permutations. And what you end up is building up this distribution of the performance of the model. So we'll take a look at this, and hopefully, at least for this, data set. So it ran 1,000 permutations right here. Right? So that was as simple as using this one line to say, give me my score, give me my permutation scores, and give me my p-value, using this k-nearest neighbors and my data. So one of the things it does is we've set CV to none, so it uses an internal default cross-validation thing when it finds none to get at this. So it says my classification score is 92%, and the p-value is 0.0009. Now, your p-value can never be smaller than 1 over the number of permutations you have. So that's a limitation, that's your smallest p-value you can get. So when you're doing a permutation test, you're actually getting an exact p-value off of it. It's not a p less than 0.005. It's an exact p-value. And we can look at this through a plot. So this is the distribution of this data. And even this is interesting, right? So that's your random permutation. So where would I have expected the mean of that distribution to fall if my data was truly randomly distributed? So center should be at 0.5. Well, so the peak should have been at 0.5. So this is on my permutation, right? So my actual answer is here on the data. This is all on my permuted labels. So what was my permuted labels trying to get at? The null distribution of my data, right? And given that this is a binary classifier, my expected median of that distribution should be at 0.5. It's 50-50 chance. So what this tells me, and this is why it's useful to look at even null distributions or through a permutation test, is that the data set itself has certain biases in it. So the data set itself has a bias towards having more samples that are on one side of the classifier than the other. So with certain data sets, you'll run into extreme versions of this, where you have highly disbalanced data sets. So one set of samples is much fewer than other sets of samples. And then you should use methods to balance that out a little bit, because otherwise you will be biased towards. So I'll give an anecdotal example. We were predicting tumor in brain images. So which voxels contain tumor and which not. And we had slices of brain images because these are surgical scans, so in-plane resolution of images is higher than the thickness. So the number of slices that are required in typical clinical settings is much smaller than we do in research settings. And so we were doing a 2D classification. And what we did was we basically took all of our data sets and said every slice is a training image. Now, tumors don't span the brain. So in our data set that we crafted, there were a much smaller set of slices that had tumors in them than things that didn't. When we give that directly to a classifier, the classifier is more biased towards saying you don't have a tumor than you do have a tumor. So balance in your data sets is kind of important. In fact, we even did something further, which is we took patches of brain. It's just random patches of brain, and some of those patches had tumor in them, and some of them didn't. But there are many more patches again. So we created an even more extreme disbalanced data set. And when you do that, basically the classifier says nobody has a tumor. Because that's its best metric by which it measures itself. The errors that it makes on the ones where there was a tumor, it says that's noise. I'm better off just saying nobody has a tumor. And that's where these classification metrics come into the picture. So you can bias the classifier to say, I'm going to penalize those where it makes an error a lot more than the ones where it's not making an error. Right? So I'm going to say, I want to force you to say things have a tumor. So those are things that one can play with in terms of maximizing things. But coming back to permutation scores, generating this distribution is nice. Looking at where this is relative to that distribution tells you how performant your algorithm was. And this is really saying that through this cross-validation scheme I'm getting, so this is a fairly easy task for this classifier. It's not only getting reasonably good performance, now again, reasonably good, I don't know, maybe the human does 100% accuracy or biopsy does 100% accuracy. Don't know the answer there. But by standards of classification, it's pretty good. The distribution tells us there is some bias in this data set. But what you can also do is, instead of getting a single number over here, you can get a distribution over there through the subsampling of training and test data. This is on all the data. That's my performance on all the data, and I'm comparing it to the performance. Actually, that's not true. Let me take that back. This is on the split that was created. But you can have a system where you have performance on unseen data and train on different data. Yes.
So in this simulation of the computation score, right, did you set that bias in the
No. that came out of this data set. We did not set. So as far as the simulation is concerned, I should say simulation as far as this is concerned, all this is doing, this permutation test score function, is it's taking those labels and randomly permuting them and generating a classification accuracy. And it's doing that for 1,000 of them. So the fact that it shows up not centered around 0.5 suggests that this data set has a bias towards one of the categories. What one can do is to change your model to account for that bias. So we haven't done that here, but that would be a nice exercise if you download these tutorials and do, which is change the model so that it gets balanced data where you have
real life data.
Yeah, this is real life data.
Where is the bias coming from?
So this bias probably says that in this data set I have more categories of one sample than the other.
So that's going to go up the bias.
Yes, at least that's what that distribution is telling us. All right, exercises. So it's 5:07. I'm going to stop here. Partly because I haven't seen that the Learn tutorial loads up still. It was giving some error earlier. So if people are stuck, we could go through this today. But it's also a time when you could relax, you had a long day, and you can enjoy socializing around here. I'm going to ask Eric if there are things that... So I can continue. I can also have them all relax. It's been a long day.
I think we can let them relax.
Okay.
I've got a bit of stupid stuff.
Okay.
So,
All right.
long day for you too.
Yeah. Glad I'm standing over here. This is for me to reset my clock. So quick question. Because there are fewer people who are doing brain imaging, to what extent do you want me to cover the Learn tutorial tomorrow morning? We do have a busy schedule with the reproducibility stuff as well, which is going to take some time. But I can spend some time, much like this, going over the Learn tutorial. It probably will take 30 to 45 minutes. If there is a reasonable interest, I'll go over it first thing and then get on to the reproducibility pieces. So you guys have all night to decide. You can tell me tomorrow morning. So are there any questions on anything we've covered so far? Are there